So thank you, and I thank you for all of the organizers for inviting me here. This is one of the best places to write algorithms on linear differential equations with the city of Limoges, of course. And so this is a joint work with Thomas Dreyfus, and I'll be using the words reduction, reducible, and in various senses. So I'm going to explain the outline of at least the scope of the talk, and as usual, I will do the easy parts, and the hard parts, well, you have to read the paper. So we're going to be studying a problem like this, and I'm going to save it on the blackboard for future reference. So we have a system written that way, y prime equals a y, and it's a reducible system, so it's of this form. Oh, sorry for that. Yeah, in front we don't really know where left or right are anymore. So, we're going to be doing the following. So we assume that the diagonal part is in a reduced form somehow, and I'll explain later what that means. So it's a desirable form. And the goal is, if this is in a desirable form, then how we put something like this in a desirable form. And if you can do that, I'll show later that you can actually produce such a reduced form for any linear differential system. And the other constraint is that I want my computer to be able to do that. So I'm going to show you something which is a real algorithm. One you can compute actual examples with. So the outline is the following. I'll give a little bit of motivation on why we got interested into that problem. I'll explain what we mean by reduced forms of linear differential systems, and so you will hear yet another definition of differential Galois groups. And we will emphasize on the fact that it's more desirable to actually compute the Lie algebra than to compute the group directly. And after that, I'll show you how to actually compute a reduced form for a linear differential system. So first, some motivation. So if we have a reducible system like this, well, there are there are many places where those kind of systems appear naturally, but one occurrence is when you study nonlinear differential equations and you happen to know one solution, and you write variational equations along that solution, and the properties of these mirror general properties of the nonlinear equation. It's a wonderful industry, and if you do that, you get systems that are very structured and that look like this. They come up naturally. So you want, in this case, fast algorithm to handle these systems and to make them as simple as possible. And I'll give a precise meaning to that. And also something that was shown to me by Clemens Raab here and Johannes Blumlein and Carsten Schneider and many others. If you have a system depending on a small parameter epsilon like this, and you want to write down an epsilon expansion of a solution, then you get a sequence of linear differential systems which turn out to have a structure like this as well. And again, if you have a good reduction method to simplify them in a sense, that greatly helps. And another thing which has been, so I've put a few names here, but really lots of names are missing. When you play, for people here and in the other rooms who play with operators from combinatorics, statistical physics, from etc., the minimum operators of generating series very often are factorized into smaller bits. And somehow you can find the properties of the factors, and it would be desirable to find the properties of their product. And so this is also what we aim at providing with this. And something I didn't write, there is a philosophy behind that. If you have a system like this, and suppose I say this is in a desirable form, so suppose you know how to solve that in some class of function, then what I'm saying looks useless because we know how to solve that system. You just do variation of constants and then you solve that system here. Except when you do that, you would have to integrate solutions of that system or that system. And the solutions could be in complicated classes. So we'll replace this operation with eventually reducing that to computing rational solutions of some auxiliary linear differential systems. So in a way, what we're doing here can be also a way of writing algebraic dependence properties on integrals of definite functions. So that was the motivation. And now the word Galois group is going to appear again, and I'm going to tell you what we mean by reduced forms of linear differential systems. So I've put the definition of a Galois group again, just in case. So we start with a linear differential system like this. We have the coefficient field is called K, and a Picard-Vaisseau extension is an extension field generated by a fundamental solution matrix, such that we keep the same constants. And the differential Galois group is the group of automorphisms of that extension, which commutes with the derivation and fixes the base field. So because it fixes the base field and commutes with the derivation, it's going to send a solution to another solution, and which means it acts on a vector space, so you can view it as a group of matrices. And because the world is well organized, it's actually a linear algebraic groups because it preserves the ideal of all relations among components of a solution matrix like that. So knowing the differential Galois group, it's a classifying object. It's knowing every kind of relations you can have among solutions. Now there's another object. It's a linear algebraic group, so it has a Lie algebra, which is often called the Galois Lie algebra. And it measures the transcendence of that Picard-Vaisseau extension and says also other things about solutions. So there has been many algorithms designed to compute Galois groups, and my favorite actually is the one by Ruyong Feng right here. He doesn't like me to point, but it really is. And but it's not an algorithm you can really implement. And somehow it turns out it's much easier to compute the Lie algebra of the Galois group than the Galois group itself. And the reason is that the Galois group is something you find from the solutions, which you don't have. And the Lie algebra is something which, if you're careful enough, you can read from the system. And that's the thing you have. So that's what I'm going to try to convince you of. And so now we go back to the 60s, and this is James Weil, somebody whose name is almost like mine, and a wonderful physicist apart from that. And they noted that if you decompose a matrix, if you have a matrix of a system, and you decompose it as a sum of a combination of constant matrices, so you find the basis of the vector space of the coefficients on the constants. So you write it as a combination of mi's, and you look at the vector space generated by these matrix mi's and their brackets and the brackets of the brackets and so on, so the Lie algebra, and you find the smallest algebraic Lie algebra that contains that, so it has to be the Lie algebra of an algebraic group, a linear algebraic group, sorry. And that's we'll call the Lie algebra associated to the matrix. And Weil and Norman noted that if this, and Magnus and Feynman and others noted that if this Lie algebra has good properties, like if it's solvable, you can actually write down the solutions of the systems by products of exponentials. And this is something we will not do here, but we will use this kind of decomposition, and I will use a very trivial example. If I start from a matrix like this, it's x times this matrix plus x squared times this matrix. If I take the bracket of these two, I get this one, and now it's closed under the bracket. So the Lie algebra associated to this matrix is SO3. So far, so good. And Kovacic and Kolchin noted something which differential geometers actually already knew in another context, but that if you look at this Lie algebra associated to this matrix, the the Galois Lie algebra of the differential system is included in the Lie algebra associated to the matrix. And it's actually it's not difficult to prove. It won't be a surprise. So in the example where the Lie algebra was SO3, what this shows is that for the differential system that has this as a matrix, the Lie algebra of the Galois group lives inside SO3. And so we'll say a system is in reduced form if we have found a linear change of variables so that the resulting system has a Lie algebra associated to its matrix, which is the Lie algebra of the Galois group. That's pretty much the smallest Lie algebra you can transform to. So to do that, we'll do gauge transformations. So gauge transformations are transformations the form y equals p times z, with p in GL n k, and then we have z prime equals some matrix p of a z with p of a, which is p minus 1 ap minus p prime. So among every transformation matrix you find of this form, we want to find one that has the smallest Lie algebra associated to it. And we want that because, first of all, because it's lovely and beautiful, but also because this smallest algebra shows really the integration pattern you need to follow after that. So then there's an additional theorem of Kolchin and Kovacic. So Kovacic is the man here. Not only the Lie algebra associated to the matrix A contains the Lie algebra of the Galois group, but there exists in theory, a change of variable like this, so that the resulting system is a reduced form. So that's an old result. There's been several proofs of that. And what we'll achieve today is to show how to compute that. And at least a part of it is simple. So that has kept a number of people busy for some years now. And I've been involved in several of these works. So in particular, if we have, say, a block of irreducible things on the diagonal, then there is a method with Barcatou, Clouseau, and Divizio, and myself that can compute a reduced form for these, and it's a rather different story. But we can assume we have that. So now I'm going to really handle that problem and then show how it does everything we wanted. So the first thing, we assume so we have this diagonal part, and then we have the off-diagonal part here, and we assume that if there was no off-diagonal part here, we assume this part is in reduced form. So if I do this Weil-Norman decomposition and I look at the Lie algebra generated by this, I get the Lie algebra of the Galois group of that system. And now we'll see how, if we know that, we can put that into a reduced form, and somehow I'll show how it gives a general reduction algorithm. So the set of off-diagonal matrices, we'll call that H sub in what follows. And the first observation is that there exists a gauge transformation of the form identity plus a matrix of that shape, so that the resulting system is in reduced form. And I will not give you a proof, but I will give you at least an argument. If there was something on a diagonal that transformed the system, because you assume that this was in reduced form, somehow you could take the inverse of that thing. So as this is already in a desired form, you don't need to change this, and you just need to act on this. So this is why you can put it like that. Of course, the proof is a bit more elaborate, but that's really the spirit. And a way to characterize that you are in a reduced form in that way is if you take the Lie algebra associated to the matrix of some transformation like this one. It's a reduced form is when you take any other matrix of that form, you get an Lie algebra which is either the same or bigger. So somehow we will use this minimality idea by trying to find transformation that project into a Lie algebra which is always smaller and smaller. So now this is the point where start of the audience can start dozing given the hour in the afternoon. So you have two very simple calculations that can keep you awake. And they really are simple calculations. If you take a matrix like this, the first thing you can note is that these off-diagonal matrices, they have wonderful properties. If you multiply two of them, you get 0. If you take the square, you get 0, and so on. So the inverse, for example, of this is going to be identity minus the sum of the FIBIs and so on. So if you use these identities, you can take this seemingly complicated expression, but this is easy to find, this is easy to find, and you see that the image of this matrix under this gauge transformation is the matrix itself, plus a sum of the brackets with the diagonal, and then something with a derivative. So somehow, if we want to make the matrix simpler, we have to adjust this thing so that when you have this expression, it will kill some of the terms in there. And another calculation which is easy to do is if you do the bracket with the diagonal here, you get also an off-diagonal matrix of that shape. So everything here creates matrices of this shape. So really what will govern the reduction, it will be this adjoint action of the diagonal part on the off-diagonal matrices. Okay, so that was the first easy calculation, so I'm going to show you an even easier one. It's a sub-problem, but that contains the spirit of what we'll do afterwards. If you have a system like this, and you look for a transformation that will send it to a system like that. So again, you take it of the form identity plus 0, 0, 0 beta. And again, it's a calculation you can do. You can compute these things and try to see what are the conditions on beta so that this is sent to there. And the condition is here. You have beta prime equals some linear expression in beta plus the right-hand side. So deciding if I can remove this part under the diagonal essentially means finding a rational solution to an inhomogeneous linear differential system. And at this point, you have to believe me, we do have an algorithm that does that, and if you don't believe me, it's written in papers. It exists. There are actually many good algorithms to do that. And in fact, we're going to need something a little bit more general. If you have a linear differential system with a matrix psi and a number of vectors on the right-hand side, by solving a parameter linear differential system with the right-hand side, we mean finding all tuples of constants and the corresponding rational solution such that this system has a rational solution. And again, it's a very simple exercise to show that if you have an algorithm that does that, you have an algorithm that does this. Essentially, you just add the ci's as new variables, and you add the equation c prime equals 0. And you get a very nice homogeneous linear differential system, and you solve it. So what I'm going to claim now is that the problem of reducing that system and computing the differential Galois, the Lie algebra of the differential Galois group there, essentially will reduce to problems like this, to a sequence of problems like this. And here is how it goes. So it will, because we have, you see, we have equations with the derivatives of the coefficients, and then we have this adjoint action psi, and somehow we want to remove parts from the matrix A here by letting this operator act in a good way. So we will look at this psi, the adjoint action, on the off-diagonal matrices or on the k point of the off-diagonal matrices. So if we have a vector space, so this is a structure of a C over the constant, and we will call it a psi space, so it's somehow stable if its image is stable modulo extension with by scalars, because psi extends a C structure to a K structure. And the reason why we're doing that is that if we have a reduced form, it can be shown that it has to be stable under this adjoint action. So somehow we have this linear algebra problem of finding all the spaces that are stable under this action here of several matrices. And once we find these, we would try to project on those spaces. And if we can do that, we get a reduction procedure. So that's an unreadable slide, but you actually, well, at least some of you know that, and if you don't, it's almost as if you did. You can always, the isotypical decomposition means that the matrix of psi, you can write it as a direct sum of blocks like this. And so the reduction process will be done in parallel on each block. So they're inequivalent blocks. Inside the blocks, there is the blocks will be sums of other blocks. So those are equivalent. And deciding whether you can remove some of those equivalent blocks is where you will have parameterized right-hand side, because you have to decide if there are some combinations of these equivalent blocks that can be removed. And that's the part here. Every block is a direct sum of indecomposable blocks. And then the indecomposable blocks, if you look carefully inside them, then they will be viewed as you have a flag structure like this with zeros above. And inside every level of those flags, you get this again. And you have a kind of fractal thing. So we essentially, writing down this decomposition of this matrix becomes a problem in linear algebra. Essentially, you have a set of non-commuting matrices and you want to find their invariant subspaces and classify their invariant subspaces. So this is a long and complicated way to say that. And well, there are ways to calculate those things. Essentially, it boils down to factoring some differential systems and in a good way. And now the way the reduction process will proceed is essentially, once you're at a stage like this, for example, if you're at a stage like that, deciding whether you can project on a smaller sum of combination things will be reduced to finding whether you have constants with the right-hand side like this, such that a system like that has a rational solution, and such a rational solution which will give you the projection to the smaller spaces. And in fact, and that's where that's actually several horrible parts in the paper, but going down the flag here is also something which will proceed like that. But the thing is that you see that we have reduced that to, first of all, a problem, finding rational solutions of linear differential systems, which is a really relatively efficient class of problem. And also the size of the problem is reduced every time we do that. So the problem of reduction, of computing the Galois group as this thing, has been reduced to finding rational solutions of linear differential system with parameterized right-hand side. And in general, the sizes of these objects are like 1, 2, or 3, so it's really small differential equations. And that's what makes the algorithm be quite efficient. At least far more efficient than anything I've seen so far. And that's it. Once you do that, you start from this, you apply this, you apply this, you apply this, you do all the projections, and you turn that into a reduced form. And so once we have that, the general reduction algorithm will be the following. You start with a reducible system, so you apply a factorization algorithm. There are many standard algorithms. And you write down the linear differential system in that form. And first, you focus on this part. And you apply to this part what we've just done. So you put this in reduced form. And once this is in reduced form, so you have this part. So now you add the A3. You have an S3 here. This is reduced, this is not. And you apply the method to this one. And once this is reduced, okay, now this, you see how to go on. And you go like this all the way up, and there you are. And so the result is a reduced form. It gives you the Lie algebra of the differential Galois group, and somehow it puts also, that's a bit more complicated to show, but everything you have not been able to remove are always, say, terms of the form 1 over x. So everything that remains are going to be things which, when you integrate, gives kind of logarithmic types things. And if you have a depth 2 here, you will have dilogarithm and so on and so on. So not only you get a very nice form with much more zeros and much more structure, but also it pretty much guides the computer on how to do the rest of the part of the work, which is do the variation of constants on what remains. And right, at this point I'm very happy with the results, so I'll stop there. So what do I mean by factorization? It really means starting from a system where all the coefficients are mixed, performing a transformation like this, that transforms the system into a form like that, where, where the blocks here now are irreducible in the sense that you can't write them in triangular form like this anymore. That's what I mean by factorization. Oh, it doesn't always work. That was my assumption. I'm going to write something that works for those systems. And if you take a general systems in mathematics, it's never reducible. Now, if you take the systems that are looked at by at least 1/3 of this room, they're always reducible. They're lovely. So you should have a method for those. Oh, yeah. Yeah, I have an example in my hand, right there. I can show it. And over there, sorry, the example is here. The equations are here. And actually, you can't see them, but you can see they're very small. You can certainly see they're very small. There we are. And you can solve them. I can show that to you afterwards if you want. Yeah. Well, so the question is why it's simpler to compute the Lie algebra than computing really the full Galois group in this case. Well, the Lie algebra really is something you read on the system itself, and the system is the data we have. Whereas the Galois group is something you read on the solutions, and the solutions is a data which is implicit. We don't have it explicitly. So that's why, if in this case, it seems easier that to read the Lie algebra from there. Somehow the structure, the Lie algebra really can be read in the system in a much deeper way than what I showed here. They're really linked. Oh, sure, absolutely. In that case, you can recover the whole group, because when I assume that this is in reduced form, it means I have done all necessary algebraic extensions already to put that in reduced form, and the Galois group of that system will always be connected with this assumption of reduced form, meaning the non-connected part has already been handled by assuming that this is reduced. So yes, I can recover the Galois group in that case, yeah. No, I can read it from the Lie algebra. I can read the Lie algebra first, and once I have the Lie algebra, then yeah, I can read the Galois group. It's not me, I'm not the expert on that, but many other people have methods for that.